So this universality of the boundary layer, both in the inner layer and outer layer, motivates us to derive the skin friction and shape factor correlation from an assumed boundary layer profile. And this assumed boundary layer profile is works in the same way as the Faulkner scan solutions in the laminar boundary layer case, but the solution, instead of coming from a solution, from an analytical solution of, from numerical solution of a PDE, it comes from correlations or function profiles that are fit against outer profile over here and inner profile like this over here. Okay. So what we are doing is we are assuming the boundary layer is like this. So we are assuming we have a the boundary layer profile of U plus as a function of Y plus works like this. So it is equal to U plus Spalding. So that's the Spalding's profile as a function of Y plus. All right. Plus a modification that works on the outer part of the boundary layer. So that is a value A that is yet to be determined, plus a function W of Y divided by delta. Okay, and this W is any function that can describe the difference between this profile and a straight line. So if you have a straight line, that's a continuation of the Spalding profile to the outer layer, right? And if you look at the difference between what the profile we have over here and the straight line, that's the that's something we can use to describe this W of Y divided by delta. And a popular way of describing W, and you can do better by having a better profile, but the result we get is pretty similar. It is equal to a sine square of Y over delta times half pi. So it is basically a profile that looks like that. So this is delta, this is 0, 0, and 1. Okay, so A parameterizes the magnitude of the this addition. So this profile has two parameters. What are the two parameters? Maybe it's clearer to write it as Y plus divided by delta plus, if you write the delta also in the plus unit. So what are the parameters in this profile if I fix this function? Delta plus, right? That's one parameter. And A, right? So these two profiles, these two parameters prescribes different types of boundary layer. We have discussed last lecture that if you have a bigger A, it corresponds to a boundary layer with more adverse pressure gradient. If you have a bigger delta star with the same A, it prescribes a boundary layer with a higher Reynolds number, right? So if we can numerically construct this kind of profiles for a range of A and a range of delta star, we can compute a lot of things. We can compute, for example, what is the corresponding shape parameters, right? We can compute what is delta, what is theta, what is delta star for this kind of profiles, and therefore we can compute what is the corresponding H star. We can also compute the skin friction coefficient, right? We can also compute, it's not directly from this profile, we cannot compute the dissipation coefficient, but with some assumption of not only the velocity profile, but also how does the tau, the renal stress, or the total stress varies across the boundary layer, we can also compute CD.